In this video, we want to algebraically determine where this function is continuous. Now, this is a piecewise function and it has 3 pieces. With a quick analysis of each piece, we can see that we have a quadratic function here, which is a polynomial. We have a linear function here, which is also a polynomial, and then another quadratic here. So individually, we know that all 3 of these pieces, they are continuous over all real numbers because they're all polynomial functions. However, we're graphing only pieces of each, and so we need to determine if the function is continuous where the pieces all meet up. So for example, if we look at the top piece and the middle piece, we see that the top piece is for x values less than 1, and the middle piece is for x values greater than or equal to 1. So essentially, we need to verify that the first 2 pieces of this piecewise function, we need to verify that they are continuous at 1. So to do this, we are going to go back to our 3 conditions for continuity at a point. So we're checking for continuity at x equals 1. And that first condition is that the function has to be defined at 1. In other words, we need to have a value at 1, or an output. And for this particular piecewise function, you can see here that this second piece is for x values greater than or equal to 1. So we know the function is indeed defined at 1. If you wanted to go one step further and find the actual value, you know that you would substitute 1 into the function 10 minus x, so that would be 10 minus 1, and we would get an output of 9. So yes, the function is defined at 1. The second condition that needs to be met is that the limit must exist as x approaches 1. So the limit as x approaches 1, that limit must exist. So I'm not sure what that limit is or if it even exists. So let's verify that the limit does exist by looking at the one-sided limits. So first we need to find the limit as x approaches 1 from the left. So again, because we're on a piecewise function, if we're going to find the limit as x approaches 1 from the left, then we need to look at the x values smaller than 1. When x is smaller than 1, that means we are on the top piece, the x squared plus 3 piece. So we're really going to be computing the limit of x squared plus 3 as x approaches 1 from the left. Doing direct substitution will give us a value of 4. So the left-hand limit is equal to 4. Now we'll move on to the right-hand limit, the limit as x approaches 1 from the right. So again, if we're looking at the value of the limit as x approaches 1 from the right, then we're needing to analyze x values larger than 1. And you can see here, when x is greater than or equal to 1, that means we're on the second piece of this function, the 10 minus x function. So we'll analyze the limit of 10 minus x as x approaches 1 from the right. Doing direct substitution shows us that the right-hand limit is going to be 9. So since the left-hand limit is 4 and the right-hand limit is 9, that tells us that the limit as x approaches 1 of this function, the limit does not exist. Now, if the limit does not exist, that means that the function is not continuous at 1. So we can say f of x is not continuous at x equals 1. And we just proved that algebraically. Without graphing the function, we were able to determine that f of x is not going to be continuous at x equals 1 because the limit does not exist as x approaches 1. So now we need to take a look at the middle function and the third piece, the second and third pieces, these 2 here. And we need to double check that these 2 functions meet up and are continuous at 2. So in other words, we now need to verify continuity at 2. So we're essentially going to repeat this process that we just did for x equals 1. We're just going to do it again, but we're going to do it for x equals 2. So condition 1, Again, in order for the function to be continuous at x equals 2, that means that f of 2 must be defined. In other words, f of 2 exists. So taking a look at our piecewise function, and why don't you let me clean this up a little for us to be clear. All right, does f of 2 exist? If we look at the domain of each piece, we can see that on the second piece here, the second piece is for x values less than or equal to 2. So yes, f of 2 does exist, and in fact, we could find its value by substituting 2 into the second piece of this function, 10 minus x. So 10 minus 2 gives us 8. So yes, f of 2 does exist, and in fact, the y value will be 8 when x is equal to 2. The second condition is that the limit must exist as x approaches 2. So right now I don't know the value of that limit, and in order to find the value of that limit and see if the limit exists, I need to look at the one-sided limits again. So we'll start with the limit as x approaches 2 from the left. Looking at our piecewise function, if x is less than 2, we're looking at values smaller than 2. So again, x value smaller than 2 here puts us on the middle piece, the 10 minus x piece. So we'll find the limit of 10 minus x. Doing direct substitution gives us 10 minus 2. So the left-hand limit is equal to 8. Now let's look at the limit as x approaches 2 from the right. Meaning we are going to look at x values that are larger than 2. So again, looking at our piecewise function, if x is greater than 2, then we are on the third piece, the 6x minus x squared piece. So we'll take the limit of 6x minus x squared. Once again, this is another direct substitution, so we'll substitute in 2, and we'll have 12 minus 4, which is 8. So now this time, the left and right-hand limits are indeed equal to each other. So this one has a limit that does exist, and in fact, we now know the value of the limit is 8. So the second condition has been met. The limit does exist. The value of the limit is 8. Which brings us to our third condition for continuity at a point, and that ultimately says that the value of the limit as x approaches 2 is indeed equal to the value of the function at 2. And we can see that that is true because the value of the function was 8, and the value of the limit as x approached 2 was also 8. So that tells us that this function is continuous at x equals 2. So to put everything together that we've done so far, it says determine where the function is continuous. We found in the first part that the function was not continuous at 1, and now in the second part we see that the function is continuous at 2. So ultimately that tells us that f of x is going to be continuous at all real numbers except for 1. So in other words, it's going to be continuous on the x interval from negative infinity to 1, union 1 to infinity. 1 was the only value we found where the function was not continuous.